Okay, I forgot to turn on the recorder. Now it is recording. All right, so the first thing we're going to do is to look at the behavior of the C code to make sure that we fully understand what it is doing. So I already have the whole thing compiled, and we just have to do a GDB of this particular program. And do you want me to show you line, statement by statement inside the loop, or do you just want to look at the end, the final result of running init nodes? Is there a preference? Sorry? Hmm? Inside the loop? Okay, so we'll put a breakpoint on line 22. There we go. And then we'll run the program. There we go. So now we're on line 22. Now pointer is initialized to nodes. So if I say what is pointer pointing to, it is actually saying that, oh, okay, it is pointing to nodes, which is also the same as the first element of nodes. So if I were to ask where is nodes bracket 0, it gives me exactly the same answer. If I were to say what is count, it is 4, okay, because count is num nodes, which is 5 minus 1, so that's why it is 4. So when we single step through these two lines of code, after the first iteration, we can now ask what is nodes. Okay, this is kind of handy because it will show you all the elements of nodes, the array at the same time. So we can see that the next member of the first element of nodes is now pointing to not a node location, but it is pointing to what it calls nodes plus 16. Now, this is important because this plus 16 is literally plus 16. Okay, this is not pointer arithmetic. So the question now is what is at that address? In other words, what is at the address that ends with 50? So that is actually it's the address of the second element of the array nodes. And I can double check and say that, okay, are we really sure that is the case? So the answer is yes, we are sure. Is that okay? All right. And we know that count should be decremented by now. So if I print count, it is now a 3. Is that okay? Do we have any questions about the C code on line 22 and 23? In other words, these two lines. Okay. If there are no questions, we'll continue with the loop. So now we are, going through the second, I think it is the second um, iteration. So if I look at count, I can tell. Okay, yep. Okay, we just completed the second one. So if I print out the entire array nodes, then we can also see how the first element points to the beginning of the second element. The second element points to the next element, and that one has not been initialized yet, so everything starts with a 0 because in a debugger, all locations were initialized to 0. So that means if I continue the execution again, then when we look at nodes, we will now see that the first 3 elements are now initialized. The first one, the next of the first one points to the second one, the next of the second one points to the third one, the next of the third one points to the fourth one, and we have one more iteration to go. So single step, single step, single step. So now when we look at nodes, it is now done. We are done initializing because the next member of the first element of nodes points to the second element. The next of the second element points to the third one, and so on. And then the second to the last element now points to the very last element. If you need to double check that, there are quick ways to do it because you can always just ask that question. Okay, so let me show you what I mean by that. So you can always ask, this is the second to the last element, is the fourth one. Is the next member of the second to the last element of the array nodes pointing to the address of the last element of the entire array? And the answer is yes. Are we doing okay so far? All right. And what is count at this point? Count is now 0. So that means I will exit the loop, which also means now I initialize whatever PTR is pointing to. I initialize the next member of that structure to 0. So if I were to go ahead and print PTR, it is actually the last element of the entire array nodes, And I can double check that by saying, is that the same as nodes bracket 4, or the address of nodes bracket 4? And the answer is also yes. So now we are really just putting a 0, which is already there. Okay, so we won't see any effect because the 0 is already at that location. So that means this assignment statement is not going to end up with anything that's visual. We cannot tell that it has done this work. And then also at this point, the global variable free pointer is also initialized to the address of the first element of nodes, single step. So now we can confirm free PTR is indeed the address of nodes bracket 0, and the answer is yes. And that completes init nodes. Okay, init nodes, just basically make a chain out of the elements of nodes, which is an array of struct nodes. Do we have any questions about this portion? Okay, which is using GDB to illustrate what the C statements are doing. No questions? Okay. So if there are no questions, we are going to go back to look at the C code, and this time we'll try to implement the assembly code corresponding to the C code. So to do that, I have the usual entry code. Okay, initialize the stack pointer, even though it's not necessary, we can always just do that. Load the return address into register A, decrement D, stda, that pushes the return address on the stack, jmpi to main, because your main is main. Okay, so that's the first function being called. When main returns, there's nothing else to do, so we put a halt instruction here. And now we can go ahead and define node. So the way we define the structure in assembly language is simply to remember the offset to the individual members within the structure as an offset. Value being the first member of a struct node, it is at the offset of 0 from the beginning of a struct node, and therefore it is defined to be 0. And then node underscore next is the second member. So where we can find the second member as an offset from the beginning of an entire structure is where we can find the first one plus the size of the first one. And because value is an 8-bit integer, it only takes up 1 byte, and therefore we have this one over here. And then we also need to remember the size of a node, and this will become useful later on. So this is now the offset to find the last element of the entire structure, plus the size of the very last element of the entire structure. Every pointer in TTP is only 8-bit wide, or just 1 byte, and therefore we add this 1 byte to it. So that means the size of a node is only 2 bytes. So that completes the structure definition. Now we move on to define num nodes, okay? And we can just do this, do it like this to define num nodes to be 5. And then we move on to allocate the space for nodes. There's really no easy way to do this, okay? So all you have to do is to say, okay, this is the first element, this is the second element. So I'm just going to be a little bit lazy here. The third element, the fourth element, and now this is the fifth element. There's no easy shortcut to say, okay, reserve the next 10 bytes for the array nodes, not in TTP ASM. So it's a little bit tedious here. So if I were to comment this, okay, so I can say that this byte is actually referring to nodes bracket 0 dot value. This byte 0 is referring to nodes bracket 0 dot next. And then this one is nodes bracket 1 dot value. And this one here is nodes bracket 1 dot next, and so on. Do we have any questions about line 15 to line 25 of the assembly code, how we allocate the space for the global variable nodes, which is an array of struct nodes? We do not have any questions. All right. So then we move on and define, node free pointer. So free pointer is also a global variable, and every global variable is going to be declared very similarly in TTP ASM, but because free pointer is just a pointer, it only needs 1 byte. So byte 0 is sufficient to allocate the space. The value is going to change later on. Now, I could have initialized it right here because I know what it is supposed to point to. I could also have initialized all of these bytes here instead of relying on the loop to do it. But I want to illustrate how to translate C code into assembly code, and that is the whole point of this particular exercise. Do we have any questions up to this point of how global variables are defined and allocated in assembly code? Okay, let me ask you one question. Are global variables on the stack? Do we go through the stack pointer to access global variables? The answer is no. Very good. Because the label nodes is defined to be the address of the array nodes. And then the label free pointer is actually referring to the address of free pointer as a global variable. All right, so just using a sequential order, now I can implement init nodes as a function. So typical to the way I do things, I look at all the local variables. It has two. So this is the first local variable. It's pointer PTR of init nodes. Because it is the first local variable, it is at the offset of 0 from the base of a frame, from the call frame. So that's why it's just 0. The next local variable, which is count, is going to be the offset from the base of the frame of where we can find pointer plus 1. The 1 plus is because pointer itself has a size of 1. Now we can also use a label to remember how many bytes we need for all the local variables. So this one is the offset to find the last local variable of this particular function plus the size of the last local variable for this function. So essentially LVS in this case is just 2 because we need 2 bytes for the local variables. It has no parameters, so I do not need any additional labels, because the whole point of these labels is so that I can easily refer to items in the frame. So let me just kind of give you a short quiz, a really, really fast quiz here. What is supposed to be on a frame when we call a function? Arguments, okay, and in the order of how things are allocated or pushed. So it will be the arguments and then return address, and then local variables, right? So that's important, okay? Understanding how the frame is constructed and what's in the frame is important. I'm not sure how many of you have tried out the Chat GPT tutor. It actually is functioning fairly well. Okay, I still cannot say 100%, but it's functioning fairly well, so it can help explain some of those concepts. All right, so with all those things defined, I need to, so the label definitions of line 31 to line 33, they do not do a single thing in runtime to the stack pointer. In other words, they're just saying, okay, if we need to reserve space for the local variables, we need 2. Okay, that's all it's saying. But it doesn't really do a single thing about the stack pointer. And as a result, line 31 to line 33 as label definitions actually do not reserve anything on the stack. To do that, you need instructions. So typically, we do something like this. We put LVS into a register and then subtract that much from the stack pointer because that's how you reserve space on the stack. And the typical way that I write my code is I am going to, have a matching end of this, and then also to finish the return code, which is LD, B, or C, or A in this case, doesn't really matter which one you use, LDBD, increment D. Now this increment D is actually important because according to the caller-callee agreement, it is the callee that is responsible to deallocate the return address. Now, some people may ask, but why is it the case? Okay, why can't the caller be the one responsible to deallocate also the return address? The answer is it is somewhat of a convention. Okay, in other words, If you want to, you can make the caller call the agreement so that the caller is the one that is deallocating the return address. But it's usually not done that way because there's a specific instruction called return on most CISP architecture, and the return instruction is also responsible to deallocate the return address. So in this class, we are following quote unquote that convention. All right. But because I already spelled out the caller callee agreement, that's why we kind of have to do it this way. Let me go to the tutor, okay, because I want to illustrate what the tutor can actually do. Chat GPT, and you guys already have the link to the assembler tutor. So let me go to the tutor here, and I can ask it very specific questions like, can you explain the caller callee agreement regarding the return address. And the custom GPT is already customized, using what we have already talked about in this class. So we can actually answer this question, specifically according to our understanding of the caller callee agreement. So it explains everything, um, even including, little samples of snippets of code. So that's a resource that you can use, okay, to kind of get a better understanding of the topics that we have talked about in this class. Now, do you have to use this tool? The answer is no, okay, but I'm just telling you that, there's a resource available. All right, so getting back to the code here. So this part here, is basically where the code goes, okay? Because at this point, the local variables are now allocated on the stack, which means these offsets, okay, pointer and count, are now correct when it comes to how many bytes are these particular items away from the base of the call frame. And the stack pointer does point to the base of the call frame at this point. So the first thing we need to do is to initialize the local variable pointer to be the address of the global variable nodes, okay? So I will just use register A for the right-hand side. It is just the label nodes, okay? That's a pretty simple thing to do. And then to get to the address of pointer, which is a local variable, I am going to load the offset to PTR into register B. So right now, register B does not contain the actual address of the local variable pointer. Instead, it contains the offset from the base of the frame to where the pointer is. So that means I need to add the address of the base of the frame. But because the stack pointer is currently pointing to the base of the entire frame, so that means adding the stack pointer to register B will accomplish what we need to do, which is making register B point to the pointer, which is a local variable. So at this point, a store, which is including a dereference of B in this case, will store the value of register A like that. Let me kind of pause and see if there are any questions. Because your final exam consists of pretty much the same stuff, okay? Just kind of remixed a little bit, but at the core, we are still kind of looking at code similar to what we are talking about. So that means a general understanding of what we are working with here basically means that you should be able to tackle the final exam as well. At the end of today, I can send you the final exam from the previous semester so that you guys can kind of look through that, okay, and just kind of get a general sense of what it looks like, and you can even give it a try, okay, try to find out all the parts that are wrong about the assembly implementation. All right, but getting back to this example, we are now moving on to line 19 of the program here. So this one, we can use num nodes 1 minus. Okay, remember in assembly code, it is using a postfix notation, which basically means you have to specify the values to work on, and then you specify the actual work to be done with those values. And then the left-hand side is count, which is going to be the same way. The way we access or put a value into count is the same way as pointer, because it is just another local variable. So that's how we calculate the address, and then do STBA. That will also accomplish the second line, which is line 19 in the C code. So now we are going to the while loop. So I don't know about you guys, okay, but the way I define or the way I code a while loop or any control structure is to implement the structure itself first, and then to go back and add the details to it. So in this case, this while loop is the first while loop inside init nodes. So I know this is overkill in terms of the name of the loop, label marking the beginning of the loop, but I'm using this standard here. The zero after the while indicates this is the first while loop at the top level of the function of init nodes, just in case I have other while loops, okay, that is after this. Okay, so this gives me the ability to go like, okay, are we referring to the first while loop at the top of the level of the code, or are we referring to the second, which we don't have in this case? So with everything that has a begin, there is usually an end. So we specify the end. And to make this a loop, we need an unconditional branch right before the end label back to the begin label. So that means I need to do a unconditional branch like this. And that is the structure of a while loop. So now I need to say, okay, but I don't want this to be an infinite loop. How do we get out of the loop? So the C code is focusing on how we stay in the loop. The assembly language implementation is focusing more on how do we get out of the loop. So can someone tell me, what is the condition to stay in the loop? It obviously has something to do with count, but what about it? As long as it is not zero, we stay in the loop. That is correct. So that means, to get out of the loop, we want to check whether count is zero or not. I cannot check anything until it is in a register. So that means the first thing I need to do is to load the value of local variable count into one of the registers. I can use registers A, B, or C in this case. I cannot touch register D because it is my stack pointer. All right, so we start with the offset to count as a local variable, put it into, we'll just dash it into register A this time. So init nodes underscore count, and now we calculate the address of count, and then we dereference it so that we know the value of count. So right now, register A has the value of local variable count, which means I can now compare that to 0. But comparing to 0 can be I can do it with just an AND operation, because AND AA is forcing the value of register A through the ALU, and therefore affecting the Z flag and also the S flag. So those two flags are guaranteed to be influenced by the AND AA instruction. It does not actually do anything to register A, okay, because after the entire operation on line 52, register A stays exactly the same. All I'm doing is to force it through the ALU so that I can examine whether it has the sign flag being a 1 or a 0, and whether register A itself is representing 0 or not. Okay, so that's the whole purpose of line 52. And luckily, we say, if it is a 0, let's get out of here. So that means, in this case, it's a really kind of simple JCI to the end label, because if register A is indeed a 0, it is time to exit the loop, and the exit point is marked by the label on line 55 at this point. So this gives me the overall control structure of the while loop. In other words, I have just implemented line 20, 21, and line 24 of the while loop. I have not yet implemented line 22 and line 23 because that's the body of the loop. Are we good so far? Okay. So if I were you in the final exam, when I'm checking the validity of the code, I would do it in a structured way as well. Okay, which also means having a marker so that you can keep track of which part of the program is already checked out, and you have done all the corrections already. That can be very useful because you're not going to be sequentially or linearly looking through the code. So that means bringing in a marker to mark which part is already checked out is good. And you may also want to bring a piece of paper that reminds you what to check. Okay, what do I need to check if it is a conditional statement? What do I need to check if it is a loop? What do I need to check? I mean, those are really the only two control structures that we have talked about: conditional statements and mostly while loops. Okay, now occasionally you might get a do while loop. Okay, but do while loops, are actually simpler in many ways compared to a while do loop or while loop. Okay, so now we go back here and backfill, and I will use indentation to basically indicate that we are now implementing line 22 and line 23. So line 22, you can look at it as two independent assignment statements, but basically we are using PTR plus one to store into PTR next, then into PTR itself. Okay, so the order of operation is to evaluate the right-hand side of the innermost part of the nested assignment statements. So evaluate this first. Okay, it looks kind of simple, but it's not as simple as you think it is. So we'll get to pointer first because it looks like, no matter what we do with this plus one, we still need to get to the value of the local variable pointer. So that's what we're going to do next. Okay, LDI, I can use register A again, init nodes PTR, add AD. So now we have the address of PTR, and then we do a LDBA. So the register B is now the value of the pointer. Okay, it is not the address of, it is the value of. The reason why I put it into register B is I think I might need to preserve register A so I don't have to unnecessarily recalculate the address of pointer later on. Okay, so that's kind of me doing some forward thinking because I look at the last thing that we need to do on line 22, which is storing something into pointer itself. So I'm thinking, okay, if possible, I would like to save the address of pointer because I need that at that point of this code. All right, so now that we have pointer, the question now is, what about this plus one? What is it supposed to do? Well, the plus one is not just adding one to pointer. In other words, if I were to use register C to represent the value of the innermost part of the parenthesized expression, okay, so I'm going to do a CPR CB first, okay, that means I also need to save the value of register B, okay, for a reason. So now the question is, what do I do to increment the pointer by one? It is not just increment C, okay? So this would be the wrong implementation because what you see here as pointer plus one is basically saying, oh, let's get to the address of the next thing that pointer is pointing to. So the distance in terms of number of bytes from where pointer is pointing to and quote unquote the next thing that the pointer is supposed to point to depends on what thing we are talking about. So can somebody look at the C code and remind me what is the type of things that pointer is pointing to? A struct node. Very good. So that means everything that the pointer is pointing to has how many bytes? 2 bytes. Okay, it is in the assembly code. There's a label specifically for that purpose. It is node underscore size. Okay, that's the reason why we need to keep track of the size of a struct node. Is in this case, I need to increment it twice. Now, this is really bad coding in terms of style because this is making the assumption that the size of a node is 2. What if I want to include another member in a struct node? Then I have to remember to come back here and fix this code. So that means that may not be the best way to do it. So instead of doing this, okay, I will comment out the code instead of actually deleting it so that later on you guys can just kind of compare the two approaches and then you can try to convince yourself that one approach is better than the other one. So instead of doing this, I'll do LDI C with node underscore size. and then I do an add here because register B has the address of has pointer itself. So if I were to add B to C, now C point is PTR plus 1. It is corresponding to PTR plus 1 on line 22. I'm going to pause here because there are a few tricky concepts here. So I want to pause to make sure that we are good to go before I continue with the rest of the implementation of line 22 in the C code. So are we doing okay with this? All right. So assuming that we are doing okay with this, is everybody convinced that line 58 to 60 in this instance, okay, is going to do exactly the same as line 61 and 62? Because we know that node size is 2. But it is very brittle coding, which means if I decide to change the structure to also have some additional members, then node size is not 2 anymore. But when you look at line 59 and 60, they do not mention anything about node size, which means if I change node size, that code will then be incorrect. And if I don't remember to change that later on, that will lead to a lot of problems, okay? Because it's not uh, obvious. But if I use line 61 and line 62, as long as node size is updated correctly when I define the labels, I can keep line 61 and 62. They will continue to work. Okay, so this part is about coding style. It is not about the correctness, because in this particular case, line 58, 9, and 60, they are correct. Okay, it is just that they're very brittle. This coding style is very brittle. All right, so we got this done. So now we want to use it to update member next of whatever PTR points to. I believe that I do not have enough registers to do this because at this point, register C is uh, the expression here. So that means, and then I need the address of pointer as well as the value of pointer. I just ran out of registers. So when I run out of registers, there are two ways that I can think of, which is one is to push the value of a register that I need to reuse again later on onto the stack. So that means I need one instruction to push it on the two instructions to push it on the stack, which is decrement D and then the store to D, to push the register on the stack. And then later on, I need two instructions to pop it from the stack, which is LD and then an increment D. Okay, so I need four instructions altogether to save and pop. Okay, but to recalculate may not be as bad. Okay, so if I look at the registers that I want to keep around, and go like, okay, which one is the easiest to recompute? Well, it looks like the address of pointer is the easiest one to recompute. So that means register A is the one that I can sacrifice at this point because it doesn't take long to recompute that one. So I'll go ahead and destroy that one, okay, because I need now to get to the address of member next of the structure that pointer points to. Okay, so where is the address of that structure? We have register A, B, and C right now. Okay, can somebody tell me which register has the address of the structure where the next member is the one that I want to modify? All right, so from the absence of responses, this means when you are coding and also when you're in the final exam, it is important for you to keep track of what is in each register. So by the time we get to after line 55, A has the offset to get to PTR. Line 56, A has the address of PTR, which is not the address of the structure that we want to modify, okay? And then by line 57, register B has the address of the structure that we want to modify. So the answer is register B contains the address of the structure itself. So that means right now what we need is to say, okay, we don't have enough register. We're going to have to recompute the address of pointer itself later on. But we're going to destroy register A. We're going to overwrite register A, and this time we'll overwrite it with the offset to the member that we want to modify, which is next. So now register A is the offset from the beginning of a struct node to member next of the same struct node. And to get to the address of the member, we now have to add B to A, because register B contains the address of the structure itself. Register A contains the offset from the beginning of the structure to the member next. So when the sum of these two become the address of member next of the structure that PTR is pointing to. Are we doing okay so far in terms of just understanding my explanation? Okay, once again, I did not write any comments here because that is for you guys to do. As you go over this code after the class and comment these lines of code, hopefully you will get a better understanding of the code, because when you are writing something in your own words of what the code is supposed to do, that exercises a different portion of your brain, and it kind of builds additional pathways to these concepts. And the recording is still going on, okay? So that means you can actually go back to this exact point in time in the recording in order to figure out, okay, but what did tax say about this line? Well, guess what? Everything is recorded. You can also draw a picture, okay? Later on, we'll also look at it from a pictorial perspective. Okay, so register A has the address of member next of the structure that pointer is pointing to. And what do we want to do with it? Oh, right, we want to store whatever register uh, we want to store whatever register C has at that location. So we want to do STAC. So that would accomplish this assignment operation. The nested one is now done. So now we just have the outermost one to be done. It is going to store exactly the same value, which means register C stay put, okay? Because it is still representing the value that we want to store. It's just a question of where do we want to store it? This time we want to overwrite local variable PTR. We had the address of PTR up here in register A, but we destroyed it already. Okay, we have overwritten it because I ran out of registers. So it's just a matter of, okay, let's just recompute it back into that register. Okay. So now we have the address of local variable PTR back in register A, and I just need to do another STAC in this case. So now we have the entire line 22 of the C code implemented in assembly code. Do we have any questions about the block of code from line 55 all the way to line 68 in the TTP ASM implementation? So there are two questions that I think you should ask in your mind. One is, do I conceptually understand what needs to be done? Because that's a much more important as opposed to, okay, what about the details of getting it done? Because conceptually, if you know what needs to be done, offsets versus addresses, um, offset of a member of a structure versus the address of the structure itself, and so on. If you understand all of those concepts, then it is just a matter of tracking the assembly code to go like, okay, I get what this code is supposed to do. And then the second question really is, if I look at this code, can I figure out what this code is doing? In other words, if I tell you that line 55 to line 68 is supposed to implement line 22, can you document the registers and double check everything to make sure that line 55 to line 68 is doing what line 22 of the C code is suggesting? So those are the two questions that only you can answer. I cannot read your mind. I cannot answer those two questions. Okay. All right. So I have written a whole bunch of code already. I think it's time to put a halt here. so I can actually debug the program. Now, to debug a program like this means that I need to know exactly what the program is supposed to do in order to understand whether it's getting it done correctly or not. Okay. All right. So let's go ahead and draw a map of this structure here. So to do that, I am going back to my Google Drive. I will start a document for this particular class. Let me see, is that the best way to do it? Okay, I think that will work. That will work. Or better yet, let me see. Uh, yeah, I should document it first. Okay, so let me just kind of go through that process. So when you are implementing the programs that you are supposed to be implementing, I also suggest using a similar step to do it, which is basically write some code, okay, and then just go like, okay, I need to double check that my code is working correctly. So I will name this spreadsheet based on today's date, 2024. This is 1202 already. And for the purpose of looking at what is in what location, I'm going to start with location 255. And then the next one down is this location -1. So I'm just going to look at a bunch of these locations, not a whole lot because I really don't need a whole lot. And then I look at the decimal to hexadecimal version of the same value, just so that, because the tracer is going to report everything in hexadecimal. So it's kind of handy to have the hexadecimal representation here. So from the stack perspective, the very first location of the stack is used as a return address from main to the entry code. So that's what it's used for. The next two, oh, I cannot really test it yet because I haven't done main yet. Okay, so we'll deal with that. So the second one is going to be, so I have to finish at least that part of the program. So this halt instruction will stay here, but I still need to finish main because main is not done yet. So main in this case has no parameters. It also has no local variables. It just has a return address. So in that case, the return code is just LDBD. Oops. Increment D JMPB. And the only thing main has to do is to call. Okay, let me go back to the C code so that you can see what main is supposed to do. The only thing it has to do is to call init nodes. Okay, so how do we call any function with no arguments in this case? Is the only thing we have to push on the stack is the return address. Decrement D, stda, jmpi to the name of the function, which is init nodes in this case. When it comes back, the caller has nothing to clean up because there were no arguments pushed in this case. So that means lines 83 to line 86 is representing line 31 in the C code. It's the simplest function call. There's no return value, there are no arguments, and also yeah, so from the caller's perspective, that's all you need to know. So now we have main. So getting back to what the stack should look like, this would be the return address from init nodes back to main. And then, but init nodes has its own local variables. So I need to look at how those local variables are declared because the ordering is based on how they're declared. So let's see. All right, so the first one is PTR, the second one is count. So when we get back here, this is count of init nodes. This one is PTR of init nodes. Okay. So now the next question is, what about nodes? Where is nodes as an array? Well, unfortunately with that one, it kind of depends on where we stash the initialization, and I can do the counting myself, okay? I would rather not to have to do it. In other words, where is this label nodes? I can actually do the counting. So let's do the counting here. This is location 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. this will be location A. Okay, so nodes is actually at location A. So now we can go ahead and document that too. So now we have, so we need 20 because it has 10 bytes, and then plus the extra thing called the free pointer. So that means we need a total of 11, 21. Well, we can always use 22 here. Okay. So I'm once again using hexadecimal representation on the other side. Unfortunately, well, that still works. Okay, that's good. Okay. So this location is going to be whatever this value is minus 1. And then I can use the same approach. And we just need 11 bytes in this case because 10 bytes for the array and 1 extra byte for the free pointer itself. Okay, so we need a little bit more down to C, B, and A. There we go. So we know that location A is going to correspond to nodes. Okay, so to be more specific, okay, let me show you what nodes actually is going to consume as a single global variable. It's going to take up 10 bytes. So it's going to take up this byte all the way to here. Those are all nodes. So if I want to use a more visual way to designate and say that all of these are really the same thing, that's how I would do it. So that's this entire region is nodes. So we can now also designate here which one is node 0. Node 0 is going to take up these 2 bytes over here. So I'm going to do the same thing. Okay, merge these 2 cells like so. This location, just location A itself or 0A, is node 0 dot whatever the first member is. I believe that is value. The next one is node 0 dot next, and so on. So let me go to column C. Column C cannot be shrunk any further because it has some long description up there. But let me just kind of show it like this and see if there are any questions about the map at this point. Do we have any questions about why nodes is starting at location 0A in hexadecimal and why it takes up basically 10 bytes? Let me just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is correct. And then right after nodes is free pointer. So this location is just your free pointer by itself. Okay. Are we still doing okay so far? Okay. So with the code that we have done so far, we have initialized the next member of the first node to be the address of the second node in the array. So the second node of the array, okay, so if I were to do it like this is the second element of the array, which is starting at location 0C. So that means I'm expecting this location to be 0C. That's the value of this location after, right before the halt instruction, we should have accomplished this. We are also expecting pointer, which is a local variable, which is all the way up here, to have the same value. So this one is also supposed to be 0C by the time we get to the halt instruction. Count has not been modified. It is just initialized to 4. So this one should be a 04. These two return addresses, I know this one. This one is supposed to be 09. It goes back to location 09, which is where the halt instruction is. This one I have no idea, okay, because it really kind of depends on the size of the init nodes, the function. So this one I just go like, whatever it is. All right, so let me see if I can zoom out a little bit. So this way we can see the entire map, or I can just remove the items that are not really needed, which are these locations. So I can take out these because we don't need that. So delete these rows. And oh, okay, nice. That gives us just enough space, but I'm gonna remove these two too because they're also not needed. So remove the same. Right, because That's the starting point. But we also know the stack pointer should be pointing to this location because the stack pointer points to the base of the frame. The frame that we are referring to would be this byte, and this byte for init nodes, because the frame of a function call provides the context of the function to perform whatever it's supposed to do, which includes all the local variables, the return address, and all the parameters. So these 3 bytes collectively is the frame of init nodes. So I'm gonna use a little bit of color coding. Okay, so we'll paint this a little bit here. So that's our frame. The stack pointer should be pointing at the base of the frame, which is pointing at location FC. Location FC should have a value of 0C, and then the init node should have a value of, count should have a value of 0, 4, and so on. Okay, so I worked this all out based on the code that I have written. Okay, I have not written this program before today. I have not run this program before today. I'm only doing this based on a simulation of how this program should work, in my mind by reading the code. All right. So the question is, does it do what it is supposed to? Okay. So now I'm going to close this one. We don't need that. All right. So getting back to the terminal, make sure I save the code first, and then go to River Spider. Okay. Submit to this is called what? Link.ttp ASM. And of course, I have to get the assembler ready to see. So we'll take a look at where the assembler is. All right. 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 So I'm going to drag it into this browser. Okay. Go to analysis. All right. So we'll check all the memory write locations or memory write operations. FF is getting a value of 0.9. I believe that is consistent with what we expected to do. The only one that is unknown is location FE. It is 4.9, but we can check whether it is supposed to be location 4.9 by going to the assemble view, because that is supposed to be the return address to main from init nodes. So um, the jump is from here. So 4.9 is indeed correct. Okay, I just double checked to make sure that the return location, which is this location here, which is also indicated by the immediate operand of line 83, is indeed 4.9. So that means, this in this case, 4.9 is supposed to go here. Okay, so that's all good. So let's take a look at the rest of the updates to memory locations. Go to analysis. The next update is FC is getting 0A. So now we look at location FC is getting a 0A. Ah, that is incorrect. I think that's because oh, right, because at that point, huh, I did not increment. I'm not storing the incremented value yet into pointer. So the question is, I'm supposed to have implemented that already. All right, this is good. The program is not working, because when the program is not working, I can try to debug it. All right, so let me go back to the C code 2. So at this point, line 22 is supposed to be implemented. And what I see is, okay, let me go back to the assembler. Okay. So when I go back to the assembler, the first thing I want to check is where is nodes, because if my assumption is wrong, then everything is off. So we have to go back and see where nodes is defined. This is nodes. Okay, nodes is supposed to be at 0A. Okay, so that's the correct assumption. But we are also seeing that in the analysis tab. Oh, okay, I know why. Because this is the first time we changed it. Okay, this is from outside of the loop. Okay, so never mind. I got it. Everything is still good. How do I know this is from outside the loop? You look at the line number. This is line number 41. So when we go back to line number 41 in the assembly code, it is right here. It is outside of the loop. This is the initialization, so everything is still good. And then the next line we should see, or the next update, is count is updated to 4. So we'll double check on that one. Okay, so we go to analysis, and this is FD getting 0 4. What is at location FD? It is count of init nodes. It is supposed to be 4 even at this point, at the halt instruction, but it certainly is initialized to 4. Okay, so everything is good up to this point. Then we go back to the C code. Okay, we get into the loop. We check to make sure that count is non-zero, which it is not. And then when we get to line 55 all the way to line 68, those are the final updates to the memory locations. So now we look for line 55 in the trace. Okay, line 55 is here. So now we actually have to start to pay attention because these are the final updates to the whole thing. Location 0B should update to 0C. We look at this and we say, okay, this 0C is indeed at location 0B. So we got that. And then, oops, sorry about that. And then we go one more step. The next update is location FC should change to 0C, which is exactly what is documented here. Okay, so there's nothing wrong with the code. Okay, I just did not remember that we have to go through the initialization before we get to the actual final update of those locations. All right, so are we still okay so far? Now, I understand that you cannot remember everything that I just talked about, okay? But do you follow the steps that I've been demonstrating? Okay, all right. So that means now we are about to implement the next line, which is just decrementing count by 1. So to decrement something, we need the address and we also need the value. So we do LDIA with init nodes underscore count. That will give me the offset. Add AD, that will give me the address. I'm going to keep the address around because I know I have to overwrite count after the decrement. So when we dereference, we're going to dereference into register B. So register B has the value of count. Register A has the address of count. Which one should I decrement? Should I decrement register A or should I decrement register B? We should decrement register B. Register A has the address of count. Register B has the value of count. The C code is decrementing the value of count itself, so we should decrement register B. So decrement register B, and then what should we do? What is the next thing that we need to do? Register B now has count -1. What do we need to do now? We are looking at the C code on line 23. Now we have count -1. What do we do with the value of count -1? No, we don't compare that to 0. We need to, all right, so what is line 23 doing in C code? This is using a compound assignment statement, but this is the same way of expressing the same thing. We have count -1 now. What do we do? Okay, we haven't decremented count. We have count -1. The value of count -1 is now in register B. So what do we do with that value? We are done with the right hand side. Okay, we are now Yep, we have to use it to update count itself. The address of count is still in register A, so that means we just have to store B back into A, or store register B to where register A is pointing to. So that concludes the loop, or the entire body of the loop, and this branch should do what it's supposed to. So when this is all done, then we have to say, okay, the member next of whatever pointer is pointing to should now be initialized to a 0. Okay, so let's see how we can do this. I am going back a little bit here to look at this code, and now I can say, oh, I cannot do that because that's just count. I have to recompute. Okay, never mind. LDI register A with init nodes underscore PTR. That's the offset. That's the address. And that is the actual pointer, okay, which is the address of a structure. I need to change the member next of that structure to 0. So now I need to load the offset into another register, register B in this case, add these two. So now register A has the address of member next of the structure that pointer is pointing to. I need to change that to a 0, okay, LDIB with a 0, STAB will accomplish the entire statement on line 25. And now we need line 26. Line 26 resembles line 18. Okay, basically they are almost exactly the same thing, except free pointer is a global variable, not a local variable. So that means it gets even easier. Register A is the address of nodes. Register B is the address of free pointer. And then we just change the free pointer to point to the beginning of nodes or the first element of nodes. Okay, same thing. And that's it. That completes the entire um, function. All right. Do we have any questions? Okay. Assuming that there are no questions, save the code, and then we go ahead and run it. And then we look at the final result to see whether things are correct or not. Okay, so now we go back to the trace. And to double check everything is a little bit tedious, okay, because what we need to do is to go from the back end up. So location 14 has the address, has 0A. So 14 is here. It has 0A. That is correct because the free pointer is supposed to point to the beginning of nodes, which is at 0A. So this is correct. Okay, we go back up a little bit. Location 13 is 0, 0. Location 13 is the next of the last element of the array. So putting 0, 0 here is correct. And then we go back up again. Location FD is a 0, 0. Okay, so we go back here and ask what is supposed to be location FD. It is the local variable count, which should eventually become 0, 0, because otherwise, we wouldn't be exiting the loop. So that is correct. And then we go back up again. Location FC gets 1, 2. Location FC is 1, 2, and that's because 1, 2 is the address of the last member of the entire array, and that is correct. And then we go back up. Location 1, 1 is getting 1, 2. Location 1, 1, which is here, is member next of the second to the last element of the entire array. It is supposed to point to the beginning of the next element, which has the start address of 1, 2. So that is correct as well. So I can bore you to death by going through all of this stuff here, but But remember, we are going backwards. So in other words, we're executing the program backwards from the end. All right. We have about 9 minutes left in the lecture of this class. Do you have any questions that you want to ask about the homework assignment? You have three homework assignments that are active at this point. The first one that is due is on Wednesday. That's the swap homework assignment. So are there any questions about the homework assignments? Mm, no questions. Are there any questions about the process that I used to develop the program that we talked about today? Okay. Any questions about the concepts that were involved in the development of the TTP ASM implementation? Okay. All right. So in that case, I don't really have anything else to say because we are done with this program. So I will zip it up and include both the C code and the assembly code and send it to you as an announcement. So this way you can have this as a reference. But once again, commenting the program is the first thing that I would do because this program is intentionally not commented, just so that you have to kind of backfill what each section of code is doing. Um, I wouldn't call this program particularly tricky. Okay, most of the things are fairly straightforward in this case. Um, and if you have any conceptual questions, I can answer those during the lab time. In other words, I will stay here during the lab time until the last person leaves the classroom. So this way, if you are in the process of writing those three programs, that you need to turn in and you're encountering a particular problem, I can take a look at your code or the symptoms of the code and give you some suggestions of what you can do. But other than that, I don't have anything else to lecture on for the lecture portion. There's no new lab, okay? So the three programming assignments that you have, those are the only thing remaining for us to do until the end of the semester. So there's no new lab, but the implementation of those three programs hopefully will help prepare you for the final exam. All right, well, I'm pretty much done with the lecture. Let me stop the recording.